Suppose x1, x2, and x3 are independent, identically distributed exponential random variables with rate lambda. Think of them as three independent lifetimes, three races, each finishing at a random time. V is the minimum of the three, whichever finishes first. W is the maximum, whichever finishes last. What are the probability density functions of V and of W? Minute and max look symmetric in the problem statement, but they need different tools. For the minimum, go through the survival function. The probability that V exceeds V. A V exceeds V means every single one of the three exceeds V. For the maximum, go through the cumulative distribution function instead. The probability that W is at most W means every single one of the three is at most W. Since the x's are independent, the probability all three exceed V is just a product, e to minus lambda V, multiplied by itself 3 times. So the survival function of V is e to minus lambda V cubed, which is e to minus 3 lambda V. Symmetrically, the probability all three are at most W is 1 minus e to minus lambda W cubed, and that's exactly the CDF of W. Two different combining rules for the same three variables: multiply survival probabilities for the minute, multiply CDF probabilities for the max. Here's the surprise. Differentiate the survival function of V, and f of V equals 3 lambda, e to minus 3 lambda V. V is itself exponential, with rate 3 lambda. That's the Memoryless property showing up structurally. Racing three independent exponential clocks and keeping only the first one to ring is the same as running a single clock at 3 times the rate. This is not automatic, it only happens because the exponential is memoryless. Try it with almost any other distribution and the minimum will not stay in the same family. Let's build f of V and f of W side by side, from their CDFs, and verify each one. On the left, differentiating minus e to minus 3 lambda V gives f of V equals 3 lambda, e to minus 3 lambda V, for V at least 0 is a clean exponential density. Check it integrates to 1, the integral of 3 lambda, e to minus 3 lambda V, from 0 to infinity, is exactly 1, since it's exponential with rate 3 lambda. On the right, differentiating 1 minus e to minus lambda W, cubed, with the chain rule, gives f of W equals 3 lambda, e to minus lambda W, times 1 minus e to minus lambda W, squared. Expand that out and you get a sum of 3 exponential terms with different rates: a lambda, 2 lambda, 3 lambda, not a single named distribution. Same three variables, same rate lambda, but the minimum stays exponential while the maximum does not. Generalized to n-id exponential lambda variables, the minimum is exponential with rate n lambda, n independent processes racing, and the first to finish wins. This is exactly the reliability testing picture: n components in a system, whichever fails first determines V, and it stays exponential no matter how many components you add. The maximum has no such clean generalization. Differentiating 1 minus e to minus lambda W to the n just produces messier sums, never collapsing to a name. So which structural property of the exponential do you think is really doing the work here?